You know, large language models are completely changing the game, but they've got this one huge secret problem, a big one. Today, we're going to dig into a really cool new method called Z-Pruner that's trying to solve this massive issue and make powerful AI way more efficient for all of us. So let's get right into it. LLMs. I mean, they're amazing, right? They can reason, they can write code, translate languages. But all that power, it comes at a cost, a really steep one. The very thing that makes them so smart, their sheer size, is also their biggest Achilles heel. So here's what we've got on tap. First, we'll break down this LLM size problem. What's the big deal? Then we'll look at the hunt for a smaller AI. After that, we'll introduce the star of the show, Z-Pruner. We'll pit it against the competition and then wrap up by talking about what all this means for the future of AI. All right, first up, the LLM size problem. I mean, we're calling them bloated, so just how big are we talking about here? Let's try to wrap our heads around the scale of this thing. Okay, get this. We're talking about models with billions, sometimes even hundreds of billions of these things called parameters. You can think of them like the tiny connections, the neural pathways in a brain. Models you've probably heard of, like Llama and OPT, are just jam-packed with them. And that's the double-edged sword, right? It's the source of their genius, but also the source of all that bloat.
And look, this isn't just some abstract technical problem. This massive size has real-world consequences. It takes an insane amount of computing power, which means you need super expensive, high-end hardware. And that sucks up a ton of energy. But here's the real kicker for you and me. It makes it almost impossible to run these powerful AIs on a device you actually own, like your phone or your laptop.
So naturally, this has kicked off this huge quest in the AI world. How do you shrink the model? How do you make an AI smaller and way more efficient without, making it dumber? And one of the coolest ideas out there is something called model pruning. The best way to think about it is like trimming a bonsai tree. A total beginner might just start hacking away at random twigs, right? And you'd probably kill the tree. But a master carefully studies the tree and snips only the branches that are redundant, preserving its health and its beauty. That's exactly what we need for AI, a masterful way to snip away the useless connections without hurting its brain power. Okay, so people have tried this before. The old school way involved completely retraining the model after you pruned it, which for these billion parameter models is just ridiculously expensive. Forget about it. So a smarter idea came along, post-training pruning, or PTP. The idea is simple. You train the model once, then you trim it. But even that wasn't perfect. Some of the best methods, like one called sparse GPT, are just painfully slow. And other faster methods, well, they often end up hurting the AI's performance, so you're stuck in the trade-off. And that is where Z-Pruner steps into the ring. This is a totally new take on post-training pruning, and it's designed specifically to be both fast and smart, tackling those weaknesses we just talked about head on. So what's the secret sauce here? Well, Z-Pruner has this really clever two-part strategy. It doesn't just look at how big a connection is, what they call its magnitude, it also looks at activation patterns. Basically, it asks, okay, which connections are actually firing up and doing the heavy lifting when the model is thinking? It's this combination of static size and dynamic use that makes its pruning so much smarter. It all breaks down into three pretty neat steps. First, it normalizes all the weights. Think of this as putting everything on a level playing field, so you're comparing apples to apples. Second, it uses a cool statistical trick called a z-score to find the connections that are true outliers, the ones that are mathematically the most important. And finally, it scales those scores with the activation data we just mentioned, so it gives a little extra priority to the connections that the AI uses all the time. It's protecting the most well-traveled roads in the brain, so to speak.
Okay, let's actually see what this looks like. So here's where we start. This is the model's original set of connections, just this dense grid of weights. Some are big, some are small, and honestly, just by looking at it, it's impossible to tell which ones are actually important.
All right, now watch this. Z-Pruner does its normalization magic. It adjusts the scale across both the rows and the columns, and suddenly you have a much fairer comparison. It's like it's stripping away all the surface-level noise to see the real structure underneath.
And this is the really cool part. By calculating that z-score, Z-Pruner transforms the whole thing. The truly important weights, those statistical outliers, they just pop. You can see them highlighted right there. These are the connections it knows it has to protect. Everything else, that can probably be trimmed away.
Okay, before we get to the results, there's one key term you need to know. Perplexity, or PPL. It sounds complicated, but it's really not. It's just a score that measures how confused a model is when it's trying to predict the next word. So, a lower score means the model is more confident and more accurate. Just remember this, with perplexity, lower is better. Got it? Lower is better.
All right, so the theory sounds fantastic, right? But does it actually hold up in the real world? Let's get to the numbers and see how Z-Pruner stacks up against the competition. And here we go, the proof is in the pudding. This table shows the perplexity scores after these models got a 50% haircut. Now remember what we said, lower is better. Just look at that bottom row. For every single one of these cutting-edge llama models, Z-Pruner gets the lowest perplexity score. It consistently keeps the model smarter and less confused than any of the others.
But what about speed? I mean, accuracy is great, but is it fast? Oh yeah, this is where Z-Pruner just blows the doors off. Check out Sparse GPT. Yeah, it's pretty accurate, but it takes over 35 minutes to prune this one model. Z-Pruner gets the same job done in under 12 minutes. That's a huge difference. It's not just smart, it's incredibly efficient. Of course, being smart is about more than just predicting the next word. This table shows how well the pruned model does on a bunch of different common sense and language tests. You can look at the individual scores, but the real story is in that last column, the average. Once again, Z-Pruner comes out on top with the highest overall average score. It proves that it's doing the best job of keeping the model's actual intelligence intact. And if you're still not convinced, this chart should do it. It shows what happens as you get more and more aggressive with the pruning, going from 10% all the way up to 50%. See that red line for Z-Pruner hugging the bottom? It stays consistently lower than everyone else. This shows how robust it is. You can chop more away, and it still hangs on to its performance better than the others. Okay, so we've seen the data. Z-Pruner is smarter, it's faster, and it's tougher. But so what? Why does any of this matter in the grand scheme of things? What's the real-world payoff here?
Oh, the payoff is absolutely massive. Smarter shrinking means we could finally run these incredibly powerful AI models right on our phones, on our laptops, without needing to connect to some giant server farm in the cloud. It means using way less energy, which is great for the planet and our wallets, and ultimately it's about democratizing this amazing technology. It's about getting it into the hands of more people in more places to do more cool stuff. And that really leaves us with a fascinating question to chew on, doesn't it? For so long, the race in AI has been about making models bigger and bigger, assuming bigger meant smarter. But maybe, just maybe, the real breakthrough, the key that unlocks AI's true potential for all of us, isn't about making them bigger at all. Maybe it's about finally figuring out how to make them brilliantly small.